Evening to everybody present over here. It gives me immense pleasure and a privilege for me, to organize, to convene this particular meeting, which you all know is, I think, the fifth lecture of this Science-Society symbiosis. Because the time has come, at least in India, that the developmental pace is tremendous. But somehow, the general people, they feel disconnected with the development and the nuances and the complexities of the technological advancement and the science behind it. So it was the earnest wish of Dr. Vittal Das Mundra, so that the general people should be sensitized about why we are calling India developing, at least in terms of technology. So that's how it started from December last year, and we have very luminous personalities giving lectures almost in every branch of science. And today also we have the opportunity of having within us another very, very famous person in his field, and also a dedicated worker, scientist, technocrat, who is also making his part in making India great again. So before we start, I will request our President, Dr. Vittal Das Mundra, to please come and take his seat at the stage. I will now request Sri Neeraj Chadha ji to please come and take his seat. And we have already at the stage, because he is the central focal point in so many discussions, even today probably, is Brahmachari Devakar Chaitanya from one of the renowned organization, from one of the renowned spiritual as well as social organization, Sri Chinmaya Mission. So basically, the plan is we should have obviously the welcome address by Dr. Vittal Das Mundra. And if you have received this, it's dignitaries introduction, convener's address, president's speech, lecture on the topic, interactive session, vote of thanks, and the biggest event, dinner. But I think what I will try to do, obviously after welcome address, we can have a convener's address, and then president's speech, because he's so busy a person, he has to leave early, and we should all listen to him, had the opportunity of listening to him. And then I will go for dignitaries introduction, Mr. Chadda's brief introduction, because if I want to give an introduction, it will be another lecture of 60 minutes, and then the lecture on the topic. So basically I will now request Dr. Mundra, Vittal Das Mundra, the president of Bharatiya Sanskriti Sanshad, as well as the other organization which is arranging it, to please address the audience. Okay.
Thank you, Dr. Dwari. I am fortunate to have blessings of Swamiji and august presence of Dr. Chadha, and my friend Dr. Devi Prasad ji Dwari is also here, and I see luminaries from Indian science in the audience. I welcome you, all of you, to Bharatiya Sanskriti Sansad and Bharatiya Vidya Mandir. Our institution, Bharatiya Sanskriti Sansad, you may be aware that it was established in 1955, and Bharatiya Vidya Mandir was established in 1948. And we have been pursuing the various aspects of Indian culture, education, training, publication, and there we have music schools and schools also, and skill development programs. So it's a multifarious task in which we are involved. This particular program, as Dr. Duwari has said, that I was feeling that the society at large and scientists, there is a gap is developing, which is not very healthy. We should know those who are giving so much, those who are dedicating their life for development of our society and our nation. We should know them, we should pay our homage to them and understand from them. And then what lies in future. It is not only today what they have achieved, what we are going to achieve, what our vision is. Modi ji has said 2047 India will be developed society, but what will be the path, how it will be, and why 2047? Beyond that also. So young generation which will be coming, what sort of nation, what sort of society we are going to live, well, all that we can discuss. And this will be a forum, although we have a very small forum here, very small place, but we welcome you with all the heart, and this place is had a honor and privilege of having hosted the lectures and talks and performances of great scholars and great artists and great thinkers. I would not take not much of your time. I again welcome you, and I will request Dr. Duwari to take the proceedings further. Thank you.
Friends, I will request Sushant Gopal Sureka to welcome the honorary guests and speakers of today's function. I request Speaker Dr. Chadda, our most beloved Dr. Duwari ji, and our President, Dr. B.D. Mudra. Now, Dr. Saab.
Yeah. Today, we are all here, as you know, to listen to a lecture on a topic which generally common people think it's almost close to rocket science, that we cannot understand, we will not understand anything about it. But the point is that this particular aspect, which will be spoken upon, particle accelerators, and their functions, applications, working experiments have now affected every branch of human life, starting from medical to other aspects, pure research, as well as other technological marvels that are happening also have sometimes indirectly, but most of the time direct applications of these particle accelerators. Now there may be one or two over here who may be thinking that accelerators, particle accelerators, am I in the right place? I know nothing about it. So basically, let me tell you, suppose I give you an imaginary ball, solid ball, and then ask you what is inside the ball, or what is the ball made up of from inside. Outside you can say plastic or rubber or something, but from inside what it is made up of. How will you tell? Suppose it has no opening, a solid ball. So basically what you do, you just cut open the ball, or if it is solid, smash the ball and try to see, test each of the fragments and say, oh, this is made up of that. Now if I take it to very, very, very small level, microscopic, super microscopic level, 10 to the power minus 8 angstrom level, then what happens? How will I identify the fragments? How will I know what is any object made up of, any atom made up of? So what they do, they also smash the atom or the molecule. But here smashing is not done by a hathodi, meaning, but it is done in a technological marvels that has been worked out in the last 70 years in machines which are called accelerators, where mostly two particles, they will come together with a tremendous speed and energy and smash against each other, and they will break apart. And the other things that comes out of that collision, scientists observe and then come to a decision about what are things made up of. So this is basically, in a very layman's language, I am a layman also, is a particle accelerator. Now, two types of accelerators. One is a straight line or a straight tower. Another is a circular thing. In circular things, you have more flexibility in terms of energy, in terms of the speed of the particles and all that. And in India, long time back, a particle accelerator, circular, which is called cyclotron, was built. It was built in Kolkata. It was built in a place called Variable Energy Cyclotron Center, which is in Salt Lake. And every Indian should be proud of the facility. But let us not talk about history. Even today, the development, the continuous upgradation, development, new technology, new concepts, new research that has created such an ambience in the VECC Kolkata that today also they are very relevant in the world stage in terms of nuclear physics and particle accelerator. Now, obviously you will be hearing everything about the societal applications, but just to set the stage without going into the detail, I mentioned about medical application, basically cancer and other things, scientific research to know much more deeper about the objects, industrial application, basically non-destructive testing of materials and semiconductor fabrication, polymer cross-linking, agriculture and food safety, food irradiation to eliminate harmful bacteria and so on and so forth, environmental protection, right? Treatment of industrial wastewater and so on and so forth. There are others, I'm not going into that. Security and defense, obviously. No, that doesn't mean that they are making atom bombs. No. Security and defense here means cargo and baggage inspection using X-rays. Every airport has. That's a part of it. Detection of explosive. Then energy and nuclear technology, new materials for nuclear reactors, research on nuclear fusion, and fission is already there for a long time. Fusion is a very hot subject. Just to give you an idea, India is trying to go to the moon and extract a little bit of helium-3. Helium-3 is called a magic element. You can have a helium-3 reactor next to your house, nothing wrong happens to you. 1.5 ton of helium-3, liquid helium-3, if brought from the moon by India, maybe 50 years later, I don't know, but it can take care of all the energy resources for 1 year for full India. That's the potential. Okay. Then cultural heritage and archaeology. You all know carbon dating, so I'm not going to that. What are the advantages? Improve diagnostics and treatments of diseases, enable cutting-edge science discoveries, support environmental conservation, strengthens national security, advance clean energy and nuclear research. What are the challenges? High construction and operating costs. large infrastructure requirement of high energy accelerators, significant energy consumption, need for highly skilled personnel and advanced maintenance. Sorry, but the future prospects, great. It aims to make particle accelerators smaller, more energy efficient, and more affordable. Compact accelerator technologies, plasma wake field acceleration, and advanced superconducting system are expected to expand application in medicine, industry, environment protection, and scientific research. Last one, advanced superconducting system. And the person sitting in middle of us is one of the master technologists of that. How many of you know? Well, generally, these machines are huge, gigantic machine. But with some initial theoretical input from a US university, just the input, not fabrication, the whole K500 synchrotron, which is a superconducting compact cyclotron, was fabricated here in Kolkata, and he was one of the pioneers. So now we know that how societal application he is giving to the society. So in concluding, I will say particle accelerators are among the most important technological achievements of modern science, one of the most. Beyond their role in fundamental research, they have come indispensable in medicine, industry, agriculture, environment, security, energy. So as accelerator technology continues to evolve, its societal benefits are expected to grow, contributing to improved lifestyle, development of the country, and regeneration and new generation of new technologies. So today is an exciting time. We are all going to listen, not in a wrong sense, from the horse's mouth. Right. So Dr. Chadda will enlighten us on these aspects, and we are all eager to know about it. And as I mentioned, time is a little short for all of us, but especially Brahmachari ji. So I will request the president of this particular meeting, Brahmachari Divakar Chaitanya, to talk a little bit about his ideas, his concepts about the topic and about science and society symbiosis in general.
Thank you so much. Om Sahana Vavatu, Sahano Bhunaktu, Sahaviryam Karvavahai, Tejasvinavadhi Tamastuma Vidvishavahai. Om Shanti Shanti Shanti. Harihi Om Sri Gurupyo Namaha. Harihi Om. It's my privilege to be over here. My humble respect and love for Dr. Mundra, Raj Gopalji, Duhariji, and our main speaker today. And when I was seeing that everyone is dear, 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 so I thought that maybe I'm the dearest one, that's why it is not written. So as I know about the things, I hesitate to tell that I'm having very small knowledge about it, because I have no knowledge about it. But the thing is, as I came to know when I was studying that what is a particle accelerator, that the scientists have invented such a mechanism when they try to accelerate the particles at the same velocity of the light, and they collide each other, and from them there no new particle come out, and some energy also comes out. Am I right? So if I tell anything else wrong, please pardon me. So this is the thing. And its implication, Dr. Dwariji has described very nicely that how the modern society can be benefited with this technology in medical field, in industrial use like semiconductors and everything else, then architectural, geological things, then in agriculture, everywhere. Now the thing is, science have invented so many things, so many basic particles, like Higgs boson is one of them. And they are, what is the main aim of science? Not only to entertain their scientific vasanas, it is not that. I think they are also trying to find out the truth. And who are with this robe, not only us, even many of you, they are also trying to find out the truth of the world. Where is the basic difference? If we say that what is the basic difference, you can say many differences. The basic difference is when science is verily interested to know what is the basic point of the whole universe, how that universe has come out, what is the thing, then Dharma Vigyan is trying to find out who am I, how I am connected with the world. One is Vigyan, another is Atma Vigyan. We can tell in that way. See, like to break a particle, the particle accelerator is required. We, the Vedantist, we also use something else, that some mechanism we are also having. And what is that mechanism? That is called body. And how we find out body, mind and intellect. And how we break that? Our mechanism is Shravan, Manan and Nididhyasan and the pure mind and intellect. So, वेदांत विश्लेषण करते हैं कि ये शरीर क्या है. Few thousands of years ago, our Dharma Vigyanis, they have invented that the body is made up of the something else, and the whole universe, the basic things are same. That is the Panchatattva. In Taittiriya Upanishad, it is thing, etasmad vatasmad akasha sambhuyate akashad vayoho vayor agnihi agner apaha advyam prithvi. So that 5 elements are there in the whole universe, and everything, this wood, this skin, everything is the culmination of that 5 elements only in various, components and calculations. We try to, we just question ourselves, who am I? What is the Jagat? What is the basis of the Jagat? मैं कौन हूँ? And Advaita Vedanta has reached in that point that the whole world is nothing but Brahman. The basis of whole universe is Brahman alone. And what is that Brahman? It is Satchidananda. What is that? It is existence alone. It is consciousness alone. And it is Ananda Swarup. It is bliss only. So, the nihilist of Buddhism, they are standing in Shunyism. That everything has come out from Shunya. 10 minutes. I will finish it up. Advaita Vedanta has acknowledged that. But Bhagavad Gita says, Na sato vidyate bhavaha na bhavo vidyate sataha. From non-existent thing, existence can't come out. from existence, how the non-existent thing come out. And Advaita Vedanta says, yes, if you are right that everything has come out from zero, who is the knower? So my point is that physics and Vedanta, where is the similarity? Both don't encourage blind faith. Advaita Vedanta andha vishwas ko support nahi karte. Each and everything, there are some questions behind it. Ko aham, main kaun hu? Who are you? You kaun hai? Who are you? Where is the relationship between you and me? So if the dharma is without the vijnana chetana, that dharma is nothing but the outcome of your emotions only. And if this science and scientific research are without dharma chetana, that can become dangerous. So both should work together, then we can see the better world. Thank you very much. Hari Om Tat Sat.
Wonderful words, really wonderful. And I was thinking when Swamiji was mentioning certain aspects, for the last 3 months, I'm reading a lot of things about what is consciousness from a very, very practical, almost materialistic point of view. Whether each one of us has a different consciousness or consciousness is a single body. The vessel, each individual. Like, for example, if you take water in a cup, in a glass, in a bowl, in a tank, the water remains the same, but only the container changes. So is it consciousness is a much more fundamental thing than earlier what we thought about. I'm not talking about perception. Perception is something which depends on the stimuli, panchendriyo, in some cases ashtendriya also. But consciousness is a much more deeper feeling. I'm trying to write an article on that, and it's an absolutely, which 20, 30 years back, I used to think, don't talk about this, right, Vedanta and all that. Oh, I don't know about it. I'm not talking about particular scriptures. I'm not talking about who said what. I'm talking about the feeling. It is not emotion. That ultimately we are reaching towards a point which nobody earlier thought science or scientists will be discussing. And for example, Roger Penrose, for the last 2 years, is only talking about consciousness. Right? If you talk about Max Born, Heisenberg, they have all spoken on this issue. So it's an amazing thing. Whatever, I should not prolong this. Now it is my pleasant duty to introduce our speaker today. But before that, this 5th meeting of Science Society Symbiosis, we think that we have got real luminaries among the audience. I counted, there are 29 people sitting here, 3 or 4 outside, maybe officials, and 6 technical people. So altogether a and 4 of us here. So altogether more or less close to 40 people, which is quite healthy, I'll say. I'll just read out the name of the persons who are very kind to grace the occasion today as attendees. Dr. Himadri Shekhar Maitri from Kalikapur. Siddharth V. Pratihar is a scientific officer in VCC. Shomita Chakraborty, scientific officer, VCC. Then I don't know whether she's here. Prapti Panigrahi, research scholar at Penn State University. Right. Is it College Park, Penn State? Okay, yeah. Well, I have been there a couple of times on astrostatistics meeting. Pritam Panigrahi, scientific officer, VCC. Dr. Hena Roy, scientist F and group head, CDAC. CDAC is a Center for Development of Advanced Computing. It's one of the cutting edge technological marvel, not only of India, but in the world. It has different offices at different cities in the country, and Kolkata one is a very vibrant. I was just talking to one of their officers. Dr. Shubhankar Mukherjee, Project Manager at OST, Central Head Secretariat, Cyber Physical System Group, CDAC Kolkata. Cyber security, but that doesn't mean that if you get fleeced by your online account or something, don't go to him. He works on a different level. Dr. Anup Ghosh, Assistant Professor, Chemical Sciences, Bose Institute. Dr. Devraj Roth, Associate Professor, Department of Mathematics, Vivekananda College. Ajayendranath Trivedi, Consultant, National Institute of Homeopathy. Dr. Parashuram Jaishankar, Scientist G, CSIR, IICB, Indian Institute of Chemical Biology. Dr. Jashwant Jaishankar, I don't know whether they're related, maybe father and son, Neurosurgeon, Kolkata. Shiv Shankar Roy, Dr. Shiv Shankar Roy, Chief Scientist, Indian Institute of Chemical Biology. Dr. Nilanjana Sengupta, Professor of Department of Biological and Chemical Science, IISER, Kolkata, rather Kollani. Dr. Amlan Kumar Roy, Professor, Department of Chemical Science, ISR, Kolkata. And Professor Indranath Sinha, Howrah. I don't have his sort of association with the institutes and all that. So now it is my privilege to talk about our speaker, Dr. Chadda. He is basically a scientific officer in the Computer and Informatics Group at the Variable Energy Cyclotron Center, plus other things. Department of Atomic Energy, Government of India. And his expertise focuses on embedded system. Right? Core competencies, embedded system, microprocessor, microcontroller architecture, hardware interface, and very low current measurement. Key projects, developed EPICS. EPICS is Experimental Physics and Industrial Control System. Architecture ported on advanced RISC machines. These are very technical terms, I don't have, he may say something. Advanced RISC machines, processors, and FPGAs. FPGAs is Field Programmable Gate Array, if I'm not very wrong. Okay, so unlike a standard CPU or GPU in your basic desktop computer that has a fixed hardware architecture, an FPGA is a configuration, it can configure its internal circuitry in the field. Almost sounds like a robotic or an AI kind of thing, but it does that to execute highly specific custom hardware used for beam diagnostics in cyclotrons. Academic outreach, he is a frequent guest lecturer and technical expert in universities, such as delivering seminars on embedded systems at Adamas and other places. He is developing hardware and embedded system, including, as I mentioned, EPICS, porting on ARM and FPGA architecture. Mentorship, he frequently guides university students and project trainees from local engineering institutes, for example, Jadavpur University, Adamas, through workshops and technical programs. But as I mentioned, he is very well known for this upgradation and operation of field mapping of K500 cyclotron and operation of K130 variable energy cyclotron technology. And K500 cyclotron, I mentioned it earlier, is the world's first compact supercomputing cyclotron, originally developed at Michigan State University and famously built at the Variable Energy Cyclotron Center. Utilizing powerful superconducting magnets cooled by liquid helium, it accelerates a wide range of ion beams from protons to uranium to high energies for advanced basic and nuclear physics experiment. And he is going to talk about not only these technical and technological complexities, but how a common man, a person like me, is getting affected in a positive way by the fantastic instruments that he and his associates are building, particle accelerators and its societal application. I will now invite Dr. Chadda to deliver his lecture.
श्रद्धेय डॉक्टर विठल दास जी मुंदड़ा, परम आदरणीय ब्रह्मचारी दिवाकर चैतन्य जी महाराज, विज्ञान जगत की सारस्वत साधना में रत डॉक्टर देवी प्रसाद दुआरी जी, मेरे आत्मीय अग्रज प्रियंकर पारीवाल जी जिन्होंने मुझे सबसे पहले इस वक्तव्य के लिए बोला, तथा श्री सुप्रकाश बोस जी तथा सभा में उपस्थित आप सभी सुधीजनों को यथायोग्य नमस्कार। अभी कुछ क्षणों पहले देवी प्रसाद दुआरी जी ने कहा कि सौभाग्य का विषय है मेरा यहाँ होना। मैं बहुत ही विनम्रतापूर्वक इसे नकारना चाहूँगा। कारण यह कि इस मंच से अतीत में जिस तरह के व्यक्तित्व के महानुभावों ने अपने विचार रखे हैं, मैं समझता हूँ कि मेरी वह योग्यता, वह सक्षमता नहीं है, बल्कि मैं यह कहूँगा कि इस मंच पर मेरी उपस्थिति ही मेरे लिए बहुत बड़े सम्मान का विषय है। साथ ही साथ आज के मेरे इस वक्तव्य की जो विषय वस्तु है, उसे आपके सामने रखना न केवल मेरा दायित्व है, बल्कि मैं समझता हूँ कि मेरा कर्तव्य भी है। और उसका कारण मैं 2 घटनाओं के माध्यम से आपको बताना चाहूँगा। जब मैंने यहाँ इस संस्थान में काम करना शुरू किया था, उसी दौरान मेरे एक सहकर्मी, उन्होंने भी साथ में काम करना शुरू किया था, श्री तन्मय दास। एक बार वो अपने किसी परिचित के साथ बात कर रहे थे, तो उन्होंने पूछा आप कहाँ काम करते हैं? तो उन्होंने कहा साइक्लोट्रॉन सेंटर। तो उन्होंने कहा अच्छा সেই साइक्लोट्रॉन फैक्ट्री, किंतु ওখানে तो काज হয় ना किछु। तो मेरे मित्र चकित रह गए कि इस तरह क्यों। तो उन्होंने पूछा আপনি এইভাবে কেন বলছেন, মানে কি করে জানেন আপনি যে কাজ হচ্ছে না? তো উन्होंने कहा कि এটা তো সাইক্লোট্রন ফ্যাক্টরি, ওই ফ্যাক্টরি থেকে ধোঁয়া বেরোয় না, তো फैक्ट्री আছে धुआं बेरोए ना, मैंने काज है ना। तो उस समय वहाँ उन्हें बिठाकर संतुष्ट करना बहुत कठिन काम था। दूसरी घटना अथवा दुर्घटना कह लीजिए, वो मेरे साथ हुई थी। हम लोगों का ही एक और संस्थान है IUAC, इंटर यूनिवर्सिटी एक्सेलेरेटर सेंटर, वो दिल्ली में है। लगभग 20-22 वर्षों पहले वहाँ पहली बार जाना हुआ था। उस समय गूगल मैप इतना प्रचलित नहीं था, तो एक सामान्य सी जानकारी थी कि जवाहरलाल यूनिवर्सिटी उसी सड़क पर किसी एक जगह है। तो एक ऑटो वाले को मैंने लिया, 2-3 बार उस सड़क को नापा। कुल मिलाकर मैं उसे समझाता रह गया IUAC, किसी तरह से वह जगह नहीं मिली। अंत में बहुत धीरे धीरे बढ़ते हुए किसी तरह बोर्ड दिखाई दिया। तो मैंने उसको कहा ये है IUAC, तुम्हें पता नहीं है? बोला सर अरे ये तो बम फैक्ट्री है। जितने यहाँ पर ऑटो वाले हैं सब इसे बम फैक्ट्री के नाम से जानते हैं। तो उस समय इस तरह की बातें सुनकर वास्तव में हम लोग हंसते थे, लेकिन बाद में जब इसे हम लोगों ने एक बड़े परिप्रेक्ष्य में देखा तो समझ में आया कि वास्तव में हमारे विभाग का काम आम जनता से बहुत कटा हुआ है। लोगों के मन में इस विभाग के बारे में बहुत सारी भ्रांतियां हैं, बल्कि केवल हमारे ही विभाग के बारे में नहीं, बल्कि अन्य कई विभागों के बारे में। जैसे सामान्यतः इसरो के बारे में लोगों की जानकारी है कि उसका काम है रॉकेट बनाना, आग लगाकर ऊपर छोड़ना। एटॉमिक एनर्जी के बारे में लोग जानते हैं कि हमारा काम है बम बनाना, एटम बम बनाना, बना के तैयार रखना। कई लोग पूछ चुके हैं मुझसे कितने बम बने, कलकत्ता में कितने रखे हुए हैं। खैर, तो इसीलिए एक तरह से मैं कहूँगा कि मेरा कर्तव्य है कि मैं किसी भी मंच से जहाँ तक संभव हो अपने विभाग की गतिविधियों के बारे में चर्चा करूं। एंड इट इज़ आल्सो क्वाइट नोटवर्दी दैट भारतीय विद्या मंदिर एंड भारतीय संस्कृति संसद, they have started this society science symbiosis, and really I feel great that I am able to put all my, not all, but at least a glimpse of the activities that we are having in our Kolkata office and some from other offices. So I'll be starting. As the title goes, particle accelerators and their societal applications. अभी light off कर सकते हैं। So if you ask a general person what is accelerator, he'll confidently answer, yes, I know what the accelerator is. He can see it in his bike, he can see in the ABC of his car operation. Yes, accelerator, A for accelerator, yes. But technically, if you ask, acceleration actually is rate of change of velocity. So, if you ask what is accelerator, accelerator is a person or machine that accelerates. But why to accelerate? What do you get by acceleration? So essentially, we'll be getting high energy, and that energy in form of kinetic energy, as the equation goes, is equal to half mv square. More will be the velocity, higher will be the kinetic energy. But then what to do with that high energy? Actually, high energy is required to break the nucleus. If you want to break the nucleus, all this kind of hammers are not going to work. As Duari ji also told, this hammer is not going to work. The reason is that all the nucleons, that is proton, neutron, the whole nucleus, it is held together by a strong nuclear force, and you require to have seriously high energy to break it or to have any modification in the nucleus structure. So it goes like this, that you develop very high energy particles, essentially charged particles. Neutral particles cannot be accelerated, or its velocity cannot be increased in that way. So we are having charged particles. For example, proton, it hits the nucleus and then it replaces some of the other nucleons, and then a new particle is created, and then it undergoes few decays, it creates different other particles, and so many other things happens. By that you can know the structure, the property, the material property of that target. So for example, this alpha decay, beta decay, all these things happens. So we are breaking the nucleus, we are splitting the nucleus, but exactly not like the fission. So we are not making atom bombs using this cyclotron. This reaction is bit different. I'll be explaining it. Then how to accelerate a particle? As Duari ji also told that एक हैमर से आप तोड़ नहीं सकते, ठीक उसी तरह जिस तरह हम गाड़ी को एक्सेलेरेट करते हैं, उसी तरह एक छोटे से पार्टिकल को एक्सेलेरेट नहीं कर सकते. So you'll require a force to accelerate a body. Where to get the force to accelerate a particle? So that force we get by electrostatic force. Electrostatic force, many of you would be knowing, and those who do not know, बचपन में आपने एक कंघे को सर से घिस कर उसके बाद छोटे छोटे टुकड़ों को, कागज के टुकड़ों को उसमें चिपकाया होगा. That attraction force that those paper clippings feels, that force is called electrostatic force. Technically, we can generate it by using these type of two plates. You apply voltage here, you put a charged particle here. For example, if you put proton here, it sees the negative plate and it feels a force to move towards this negative plate, and this attraction force that it feels is electrostatic force. So if you can apply a force, you put a charged particle somewhere inside and it will be attracted, and since it is experiencing this force, it will be accelerated. So let's accelerate a charge. The simplest method, it is same as kicking a ball. You are having these two portion of a system. This portion is more negative than this. A charged particle is coming from this side and accelerated towards this side. In between my lecture, sometimes I will be using the term charged particles, bunch of charged particles and beams. So those who are associated with the construction thing, please do not misinterpret this beam with that beam. This beam means moving charged particles. So beam of charged particles come from this side and it is accelerated to that side. But what if we require to have higher energy? Then you can multiply that kicks. One person kicked the ball, another person kicked it again, and then again. So in that way we can make such a system that one part of the system accelerated the particles, another part accelerated again, means you are having more negative and negative voltages in a series so that you can have higher and higher energy. But if you see this system, there are two problems. First, as you are increasing the system, obviously the length of the system is increasing. This type of systems are called DC accelerator, and due to its operation, they are called linear accelerator. So if you are trying to have higher energy, the length of the whole system will be quite large. For example, if you know this Large Hadron Collider, this is a linear kind of accelerator, and the length, total length is around 27 kilometers. Synchrotron in Raja Ramanna Center of Advanced Technology, I'll be telling you about it. The circumference is 180 meters, but we want to have it in our office, one office, in few, so we try to make it within few meters. How to do that? So let's make a long system short. When there is a very long length of wire, what do we do? There is a simple method. You just wind it like this. So one problem is solved, that if you are having a long system, if you can make it circular, the length can be reduced. One problem solved, but what to do with that voltage, higher and higher voltage? For that we use very famous method, this carrot method. How to do with that? You take two plates. When this charged particle is moving towards one plate, negative plate, let it come. As soon as it enters here, you make it positive and other place negative. It will see that, it will try to move there. बचपन में छोटे बच्चों को परेशान करने के लिए जो एक्टिविटी माता पिता करते थे कि एक बॉल माता जी के पास है, बच्चा उधर भाग रहा है, जैसे ही उधर भाग के आया उन्होंने पिताजी को फेंक दी, बच्चा इधर से उधर कर रहा है, वैसा ही खेल हम लोग बीम के साथ भी खेलते हैं. But in that case what will happen? Will it move from here and there? Will it just oscillate? How will it move when we are just changing the polarity of these two plates? You can have an idea by this experiment. Say if you take a metallic ball, tie it up with a rubber band and start moving it. First slowly and then at a faster rate. What you will see that slowly this rubber band is getting stretched, and when it is having quite high energy, quite high speed, it is stretched and it is rotating in a circular way. Suddenly if you cut it at some point, what you will see that earlier it was in circular motion, suddenly you cut it and it will go in a straight line. Somewhere it can hit someone's head, and suddenly your physics experiment will become biological experiment, that it has opened someone's head and you can see what's there inside. But we make it hit to a specific target. So the beam, ion beam, moves exactly in the same fashion. As it gets higher and higher energy, it moves in a spiral path, and then when it got its sufficient energy, at that time we deflect it so that it can hit a target. So in a nutshell, this is the construction of a cyclotron, that we are having huge magnets, and within this magnetic field the charged particles, they tend to move in a circular way. When that particle is here, we make this part negative, so it moves here and it enters here. At the same time we make this D2 part negative, so that it moves and comes back here. If you can just run the animation. So it moves in this way. So getting accelerated and then hitting the target. So since the polarity of these two plates are changing, alternating using radio frequencies, that is why these systems are called RF accelerators. Abhi kar sakte hain? From current slide. From current slide. Current slide. Thank you. So if you want to see how accelerators developed in India. So India's first particle accelerator was a 38-inch cyclotron, and it was conceived by Dr. Meghnad Saha in earlier 1940s. At that time, Ernest Lawrence, he invented the cyclotron, and Dr. Meghnad Saha sent his students, Dr. B.D. Nag Chaudhary and few more students, so that they can learn how the cyclotron works. They can bring back some components, and so that we can make that system here itself. They knew the potential of this machine, how beautifully and how it can be used in different parts of society and for physics experiment in particular. But as you see the timeline, 1940s, it was a time of World War, and there were lots of problems related to that. Fund was short, import restrictions were there, and the whole project got delayed too much. That was the reason that some of the parts got aging effect, some did not work, there was some problem with the vacuum technology, and that was the reason that it got its first beam after 14 years in 1954, and the research could begin only by 1966, but by that time the whole system got so much aged, and there are a lot of other problems, mainly fund, location, so many other things. But anyway, it was installed in the University of Calcutta at that time, and the problem was that it could not be used for significant research. But during that time only, Dr. Homi Jahangir Bhabha, who is known as father of atomic energy department in India, he thought of another cyclotron. Anyway, that was the image, Dr. Meghnad Saha, Dr. B.D. Nag Chaudhary, and that was the old cyclotron system at that time in University of Kolkata. So Dr. Bhabha thought of this project in 1964, and then he gave this idea to Department of Atomic Energy. Meetings happened, and at the last, in 1969, DAE sanctioned this variable energy cyclotron project to be built in Kolkata. This committee was headed by Dr. Raja Ramanna at that time. At almost the same time, Saha Institute of Nuclear Physics, it also started building in Salt Lake campus. You can see Dr. Ajit Kumar Saha. He is son of Dr. Meghnad Saha, and at that time, this whole Salt Lake area was it was just about to be built. At that time, all this construction work started. Finally, all the hard work of scientists, of engineers, of technicians, it paid off, and on June 16, 1977, this variable energy cyclotron got its first beam. The note from the director at that time, Dr. A.S. Devatia, he wrote the note, cyclotron has worked, 8 million electron volts, alpha particles were obtained, and no testing tonight. If you can just think of this word tonight. At that time, there was a shortage of electricity, lots of fluctuation. The stability requirement to run the cyclotron was tremendous. Means you'll have to think of parts per million type of stability, not in percentage. So if you are running a system which is running in hundreds of amperes, there you need to have stability in terms of milliamperes. So that was not possible in daytime. So scientists used to work in the late night, and often the people living nearby, they used to ask, ये तो रात्रि बेला की करछेन आपनी बम बनाच्छेन नाकि. बहुत सारे ऐसे वैज्ञानिक हैं जिनको लोगों ने पूछा कि इतनी आधी रात में यहाँ काम क्या हो रहा है. But at the same time, scientists were putting their body, putting their soul to make this system work, and that was the reason that this date is celebrated as the foundation day of Variable Energy Cyclotron Center. And I'm very happy to tell you that this year we had an event on June 16, that is curtain raiser of Golden Jubilee year. Means from this June 16 to next June 16, we'll be having this Golden Jubilee years. Means this year we'll be completing the first beam output of our cyclotron, completing 50 years. cyclotrons in VCC. Currently, we are having 3 cyclotrons, which is running 24/7. This is the oldest cyclotron called K130, room temperature cyclotron. K130 terms indicates that the proton can be accelerated to maximum 130 million electron volts. जैसा कि अभी बात की थी कि अगर आपको हाई वोल्टेज से केवल एक्सेलरेट करना है, you can think of having 130 million volt, 130 megavolt to accelerate one charged particle. So practically it is not possible, but using this machine, where you are rotating the particle in a circular way, this thing is possible. So it was the first research particle accelerator. Means first particle accelerator was obviously that 38-inch cyclotron by Dr. Meghnad Saha. But since research could not be done, that is why the first research particle accelerator is termed, this RTC is termed as first research particle accelerator. From its inception itself till date, hundreds and thousands of researchers, scientists throughout our country and from abroad, they have used the beam from this accelerator to have their research, to have their PhDs. The maximum magnetic field is around 1.7 Tesla, and it is a huge machine. You can think of 300-ton magnet itself. This magnet itself is around 300 ton. This is the coil, and this is the yoke part. It is called variable energy cyclotron, means if the particle can have variable energy as per the requirement of the user. The proton we can accelerate from 6 to 60 million electron volts. It has 4 experimental beam lines, and it is dedicated for low energy nuclear physics experiment, and now it is used as national facility running 24/7 for different kind of users. After some time, people thought that we want more and more energy. But to have higher energy, essentially you will require higher voltage as well as higher magnetic field. How to generate higher magnetic field? Obviously, you will have to increase the current in the coil to have higher magnetic field. But as soon as you will increase the current, obviously the heat loss will increase. It is given by the term I square R, means if you double the current, your heat loss will be 4 times. So obviously in the copper coil, you cannot have very high current. Then the scientists came up with this superb idea to have superconducting coil. So this part is the superconducting cyclotron. You can see lot of cryogenic lines, lots of helium and nitrogen lines coming to cool down the coil inside. In June 1997, the foundation stone was laid by chairman of Department of Atomic Energy at that time, Dr. Chidambaram, the director at that time, Dr. Vikas Sinha. They laid the foundation stone. The construction work started after that. This was the older cyclotron, and on this ground, the construction work started. This was the image around 2006 when the machine installation was still going on. This is the magnet. This was the magnet at that time. And some of the scientists from Japan, from America, they visited VC Kolkata, and they came to see the developmental activities. I was there somewhere in the corner at that time. Finally, on August 2009, we got the first beam. And we just celebrated it. Director at that time, Dr. Vikas Sinha, and all the newcomers faces, all the young faces that you are seeing, they are now the senior scientists and taking care of lot and lots of complex activities. If you go by the specification, it is still the most powerful heavy ion cyclotron in South Asia. Complete South Asia, if you want to have highest beam energy, you'll have to come to Kolkata. You have to come to superconducting cyclotron to have highest energy that you can get in South Asia. The magnetic field is 3 Tesla to 5.5 Tesla. You can think of that the weight, it is having quite small than the earlier cyclotron, just 80 ton, but the magnetic field is huge, around 3 to 4 times of that earlier cyclotron. And when you are making such compact system, obviously the complexity is increased in multifold. Think of this machine, the diameter of this machine is around 3 meters, but if the geometrical center of this machine and magnetic center of this machine is deviated by just 1 millimeter, the beam will not come out. And this is the fact we learned in a very hard way. For a very long time, we could not have the beam output, and thus that reason was that just 1 millimeter difference between its geometrical center and magnetic center. So the complexity, you can just think of how much precision and accuracy it requires to have to build this machine. So it is a superconducting coil based machine which is merged inside the liquid helium and is covered by liquid nitrogen. It is dedicated for medium energy nuclear physics experiment and running 24/7 to serve the users across the country. Then we thought how to give this expertise to the society, the direct benefit. But the functioning of this medical cyclotron was entirely different from the classical cyclotron. There are lots of different things, starting from its ion source, which gives the charge particle to it, how will you extract it, and so many other functions were quite different. So we thought that first we'll get a basic cyclotron so that we can understand it fully, so that we can build our own cyclotron. So at that time, the machine was procured from IBA Germany. But then, due to so many reasons, so many clearance, the project got delayed too much. And ultimately, that IBA told that, okay, you are having our cyclotron in your box, we cannot come there. Otherwise, they'll be charging exorbitant price. So at that time, our scientists gathered their courage, they got their approval, and we, the scientists in Kolkata, they managed to assemble this whole thing, and the thing worked perfectly. So it was installed in Chagaria campus, and it accelerates negative ion. You can think that in classical cyclotron we accelerate positive ion, whereas in this the ion source produces negative ions and we accelerate it. The proton beam energy is just 30 MeV. Now the question comes, if we can make 170 MeV, 500 MeV by our normal cyclotron, why not to make this 30 MeV beam? It's quite easy, no? But the beam energy what you require is huge. In our classical cyclotron, we are getting beam output in microamperes, few microamperes or few nanoamperes, whereas in this cyclotron the requirement is around 300 times more, 200 times, 300 times, 400 times, because more you are having the beam, faster you can produce the radioisotopes so that you can send it to different hospitals. So it is used for producing medical radioisotopes. It is used as a medicine for detection of cancers. So wide range of PET and SPECT isotopes are produced using this machine. And daily, the scientists get up in the 3 o'clock in the morning, they start their working between 4 to 5 o'clock. They produce the radioisotopes by 6 or 7. It goes to hospitals and given to the patients, and then the diagnostic starts. Other than these cyclotrons, in our department we are having other particle accelerator. For example, Tata Institute of Fundamental Research, Mumbai, we are having Pelletron. In IUAC, as I told, Inter-University Accelerator Center, New Delhi, we are having another Pelletron, and these are DC accelerators. As I told, this is the standing cyclotron, not circular, means this high voltage part is from the top. The beam goes up, got stripped, then comes down, and then the experiments are taken care. Similarly, in Raja Ramanna Center of Advanced Technology, Indore, we are having a third generation synchrotron radiation facility, Indus 1 and Indus 2. You can see the circumference, it is around 180 meters. In our superconducting cyclotron, the circumference is around 18 meters. It is around 10 times of that. But think of the current, it is around 300 milliamperes. If you think of all this light and this fan current, you'll not appreciate this current, but having beam of that high energy, of this intensity, is just huge. You can think of the beam energy, it is 2.5 giga electron volt. It's huge. But again, after all this complex activity, lots of effort, obviously the question comes, what is there for the society? So when you are making such a big system, you'll have to keep in mind that all the you can say benefits are not direct benefits. There are a huge amount of indirect benefits, and let me explain them one by one. If we talk about the application of synchrotron, it supports multidisciplinary research in material science, condensed matter physics, chemistry, biology, environmental science, nanotechnology, and all these experiments are directly, not directly, I would say indirectly related with the different activities that we are having at industrial level, at medical level, at different kinds of research that we need in our industry. Similarly, pelletron can be used for material characterization. Semiconductor industry, it is booming in today's age. Nuclear data measurement, radiation effect. Similar thing we have in our cyclotron. Development of advanced material. As we are growing up, we obviously need different kinds of advanced material to have research in many fields. Nanotechnology, semiconductor technology, all the things that will have advanced stage, obviously you need to have that kind of research. Similarly, application of cyclotron, if you see, material characterization, semiconductor research. For example, in our cyclotron, recently we had very special experiment that if you want to send your electronics to a space, how will that behave? Whether it will survive there or not, whether the data which you are sending here, whether it will be changed or not. All these experiments, instead of sending it there and getting failed, all those things you can do it here itself. So all those experiments we can have with our cyclotron. Ion implantation, by that you can have different kinds of magnetic, mechanical, we can change optical, magnetic and mechanical properties of the material. Radiation damage studies. Now we are shifting from thermal power plants to nuclear power plants. And when you are running a power plant, nuclear power plant, you are having huge amount of radiation there. So all the material that you are using, whether they will survive that amount of radiation or not, before making your nuclear power plant, you need to have in advance this information, that what kind of material that you can use in that type of places. All the nuclear material research you can have with this cyclotron. If we talk about technology, the accelerator technology, superconducting technology, R&D related to computer control, instrumentation. And let me tell you, when you are having this kind of technology, this technology will not be used just for your office, just for this machine. When you are giving this task to your industry, obviously that industry will develop. The skill set of the people who are working there will be developed, and they can make, rather I would say they are making that kind of machines, the structure, the product which are world quality, and rather they are exporting their product to worldwide. Power technology, as I told, we need to have ultra stability while developing this kind of power supplies. So there also our industry is growing. We are giving them our technology so that make world-class instruments. The detector technology, we are working hand in hand with CERN and many other international collaboration, and you would be happy to know that in all those research labs, the detectors are being made in Kolkata by our scientists. In field of medical, means direct benefits, we can produce different kinds of isotopes like gallium 67 and other, iodine, fluorine 18, for soft tissue tumor imaging, myocardial perfusion imaging, means overall different kinds of cancer detection. One of the most interesting and one of the most used radiopharmaceutical is FDG. But how to produce that and how it can be used, it is quite interesting to know. When you want to know where the cancer is and you want to detect it, obviously your general camera will not work because they can detect only the visible light. X-rays, they work mostly on your bones. They can give some hint of cancer, but they cannot exactly diagnose where the cancer is. And you want to diagnose, you want to know their location. So you'll have to use the property of those cells. Cancerous cells are actually the normal cell, but suddenly they have started growing uncontrollably. And when there is some uncontrollable growth, obviously they'll require to have all the resources, energy resources, and these cancer cells, they are just glucose hungry. So all the energy in our body is, it comes from, mainly it comes from glucose. So all these cancerous cells are glucose hungry, they want to consume all the glucose, and this property we use to detect where they are. But if you know the formula of glucose, it is just C6H12O6, means just carbon, hydrogen, oxygen. How can they detect this cancer? Then scientists came up with a brilliant idea. What if we can make this glucose radioactive? But how to make this glucose radioactive? Then came the function of this particle accelerator. Using our cyclotron, we can have very high energy protons here, which can hit this special kind of oxygen atom. In general, this oxygen is having 16 atomic mass, means 8 protons, 8 neutrons. But it is a very special kind of oxygen atom, which is having atomic mass 18, where it can hit, this high energy proton can hit it here. It can just knock out 1 neutron. So ultimately, we'll be having 9 protons and 9 neutrons here. And this new element will be generated, and it is called fluorine 18. And this new element, it is, or I should call isotope, which is radioactive. That is why we call it radioisotope. It emits such kind of radiation that we can detect. So ultimately, but then again question comes, how to make this glucose radioactive? So we are having this glucose structure here. You remove this hydroxyl ion and attach this fluorine 18 there, and ultimately you will be getting this FDG, that is fluoro, it comes from this fluorine, deoxy, you are removing this hydroxyl ion, and glucose, and this whole thing is radioactive glucose. But then how it works? So we inject this FDG to the patient. Cancerous cells are obviously glucose hungry, they consume most of this glucose. This FDG is get trapped inside those cancerous cell, and this FDG emits a special particle which is positron. To give you an idea about positron, हिंदी फिल्मों में देखा होगा आपने जुड़वा भाई, राम श्याम सीता गीता जैसे, एक भाई पुलिस ऑफिसर निकल गया, दूसरा गुंडा निकल गया. So this positron is the same bad guy of this electron, just in a jokingly way. So this positron is having most of the property of electron, but its polarity is positive. Electron is negatively charged, this positron is positively charged. So this positron comes out, it meets with an electron, they annihilate, they gives gamma rays in two different directions. This gamma ray is detected by this machine, and at the end you get this positron emission tomography scanner, and they can detect the cancer. So obviously the mission is accomplished. Now we know where the cancerous cells are. This is the machine that we use for detection of these cancerous cells. But again, there is another challenge, half-life of the isotopes. Obviously, you are injecting a radioisotope in the body of a patient. If the half-life means it is a time duration within which the activity of that radioisotope is decreased to half. So obviously, if you are injecting it to a patient, obviously you want that it will be deactivated very fast. But then there is a challenge that if you are producing it in some place and then you are giving it to hospital, they are injecting it, obviously it takes some time. But if you want to send it to a distant place, obviously you cannot do it. We are producing it in the Kolkata, we are trying to send it to the different hospital of Kolkata, but if we want to send it to a patient in Bardhaman or Durgapur, we will not be able to do. It will be deactivated to that extent that they cannot have this type of detection. What to do then? That is why we came up with an idea that why not make our own medical cyclotron. If we are having that type of technology, if we are having that type of know-how, why not to build our own medical cyclotron? So the efforts was initiated. The ion source is complete. This magnetic part, the magnet part is under test. The facility, the setup is almost complete, and the setup will be built somewhere around here inside VCC. And very soon you will be hearing the good news that our own indigenous medical cyclotron has started working, and will not be just making it to give isotopes to different hospitals of Kolkata. Rather, we are developing it to build a technology that we can transfer it to different industries so that they can produce this type of medical cyclotron, and we can get it installed in all the major cities throughout our country so that all the patients can be benefited with our technology. So what is there in the future for our cyclotron? If we think about healthcare, as I told, we can produce more and more different kinds of radioisotopes so that cancer can be detected at more and more earlier age so that it can be cured easily. In case of scientific research, obviously lots of research in this area is going on. Further research can be done. In case of agriculture, we can produce some types of isotope. We can be used for soil and fertilizer research. In semiconductor technology, obviously we have started using it in that way. Further and further development can be done. In the national security, as indicated by Duariji, detection of explosive and contraband type of material, forensic investigation can be done, radiation detection can be done, border and cargo security can be done using this type of particle accelerator. You might have seen a small machine. It is a linear accelerator which is used for this cargo security. Sometimes you'll be hearing that a person is having some gold or some specific material inside their belt, inside their shoes. Obviously, the general X-ray machine cannot detect that. You want to have a specific machine. They can detect the type of material that you are carrying, and these particle accelerators will be very helpful to detect all these things. When you are having a huge cargo, obviously you cannot have a simple X-ray machine. They cannot penetrate the whole cargo. It is of a few tens of meters. There this particle accelerator helps a lot. They produce those kind of particles. They can penetrate the whole cargo, and you can detect at the other end what are the materials you are carrying in that big container. In space and defense, as I indicated, people have people have started using this type of particle accelerator so that they can foresee what will happen to their techniques, to their semiconductors when they will send it to the space. So in a nutshell, cyclotrons, they are small machines with big impact, with lots of direct and indirect benefits to our society. I'll finish my lecture with two interesting facts. The first one, if you know how the public, general public, got the internet. Earlier, this internet was used by mainly US defense, and it was text-based, mostly text-based. In the CERN, Geneva, there was a computer scientist, Berners-Lee, and he was struggling a lot to share information. As you know, that's this whole research laboratory is 27 kilometers long. You are having lots and lots of computers, but obviously all these computers didn't come at a time. So they are having different architecture, different operating system, different kind of structure. So obviously if you want to share the data among all these computers, he was just struggling. Because all the systems, all the softwares, they cannot run in all the machines. So he came with an idea. He started making web browser so that this data can be shared. He started the development there in 1990. He made this first web server. And very soon in 1991, this first website went live. And as a result, the whole public got this World Wide Web, www, so that we can use the internet. If I ask today, how many of you are using internet, I would hardly get a single person who is not using internet. You got your internet in your pocket, and this is the spin-off technology of a big particle accelerator itself. If I go to the terrace of my office, present building, I get seen like this. This part is Salt Lake in 2026. This is the road in front of my office. This is the road, a flyover going from Ultadanga, then towards Baguihati and towards airport. This part is highly dense area, Kestapur. Now let me take you to 55 years back. Same scene, if you can remember. The same road coming from Ultadanga, going towards airport, Kestapur, if you can see, then you can imagine the area of the Salt Lake. It was completely marshy land. You can have snakes, you can have scorpions, all type of animal. You name a crawling insect or crawling creature, you'll get all of them in Salt Lake. So scientists say, people say that scientists did a commendable job by making a cyclotron there. But I would say, let's agree to disagree. Because the people who started working first there were these people. They struggled there to construct the whole structure there. The whole infrastructure was first built by these people who worked there for structural development, and that was in 1970s. And you'll be pleasantly surprised that at that time there was a key person who actively participated into this structural development activity. I'm talking about 1970s, and that person is present here with us in this room. And he's none other than Dr. Mundra. I'm talking about the time, 1970s, and I think it would be the initial projects when he started his career. And I can say that he has seen VCC from its sprouting state to its present state, when it has grown up to a large tree where we are splitting the atoms for the benefits of the society, for the benefits of our nation. Thank you all. आप सभी का बहुत बहुत धन्यवाद आपके धैर्य के लिए, आपके समय के लिए.
fascinating session of machines, their applications, and how it positively affects each one of us. I personally, it was a learning curve for me because we all see the applications, like this positron emission tomography and all that, PET scan and all that. But the work, the theories, the machines, the techniques, the instruments, those who have built them, fabricated them, I think they are the real national heroes of today. So it's actually, we should all be thankful to them. And lastly, which I never knew, to Dr. Mundra for taking part in the initial project. But how many of you know, just as on the passing, when you talk about Chandrayaan and Mangalyaan and PSLV rockets, we feel proud, right? Do you know the launching pad of ISRO was built by Dr. Mundra? Right. It's an amazing information for me, because both at, I think at Sriharikota and also in Kerala.
Sorry to interrupt, but this IG card Kalpakkam,
Yeah.
is participating in that.
Just imagine, right? Just imagine. So, but I personally feel proud that I'm in his association, and lot of exciting informations, and a lot of thoughts going on our mind, and our intellect is excited. So, we want to illuminate further, probably. So let us do not a particle-particle collision, but a collision of our intellect with the intellect of the today's speaker. Interactions, questions. So I will expect, if you have any queries. I think VCC people are excluded from this because you all know the answers and you know the questions. It is right. No, please. Any other person, if you sort of have any question.
Thank you very much. It's a really fascinating lecture. As Professor Durai told, Duariji told that there are many informations about you and Mundraji. And more than that, the lecture was fascinating actually. A lot of facts which I am not aware of. Of course, I'm in a different field actually, so it's very nice. So especially I'm interested to know about the applications in the medical science. You are actually producing these accelerating particles in VEC, and then you are giving to the hospitals for applications. Is it like that?
Let me clarify a few facts.
Yeah.
In VCC, we are running 2 classical cyclotrons. Means we produce beams that can be used for research in physics, in material science, and so many other things. Medical cyclotrons, those machines are different because their technology is quite different. So when we say medical cyclotron, those machines are dedicated for medical purpose only. So those are different machines. So one similar machine, it is there working in Chakgaria campus. We are producing medical isotopes using its beam. Further, one more cyclotron, MC18, medical cyclotron, we are trying to develop it, means indigenous cyclotron. So in VCC, we are not making it. In Chakgaria campus, this cyclotron is being used.
Okay, I understand. Thank you very much. So are you using the 30 milli?
30 MeV.
30
yes.
MeV? You are using for all the medical isotopes when you are producing?
No, actually different isotopes require different energies. For example, this FDG requires around 12 to 18 MeV, and that's the reason that when we are making this new cyclotron,
Okay.
MC18, it is having energy of 18 MeV. But FDG can be produced using that energy beam.
Fantastic. So if it is so, I'm sorry that I'm furthering the questions
No, no,
actually.
it's okay,
because
please.
that was my ultimate question which I'm bringing out now.
Sure.
Is it, I think, are you or the country is anticipating something like that in producing in a smaller, developing a smaller cyclotron? So
Yes,
that it will be
when we have given this idea of a 19...
on-site, it will be used for the medical applications.
Not exactly on-site. When you see, Dwari has also indicated that when you are making this cyclotron facility, obviously you require huge amount of energy. Not only the energy, when you are running such type of cyclotron, you also require different helps from different other technology. For example, you need to have cryogenic technology. You may need to have very high and very stable power supply. So you need to have some space. Obviously, it can be made compact. In the further, after this 18 MeV cyclotrons, we are also thinking of making 10 MeV cyclotron, and it would be quite compact. And obviously, if you see our earlier cyclotron, like K130 cyclotron, it is housed in around 20 meter by 20 meter room.
Correct, correct.
Further, it was squeezed to have a circumference or diameter of 3 meter only.
Yes.
When we are developing this new MC18 medical cyclotron, new medical cyclotron, its whole room is just, I think, just 5 meter by 5 meter room. So slowly we are trying to make it compact, so that obviously when we say that this technology is ready to be given to the hospital, obviously a hospital will ask how much space you want, how much energy you want.
Correct.
Accordingly, they will decide the cost of that medicine that a patient needs to pay.
Correct.
So we are trying to make it more and more compact.
Thank you. And then one more medical question,
Yes.
which you are using it, oxygen you are converting to fluorine.
Yes.
Okay. But is it very specific to the cancer cell, or it's because water is present everywhere in the body? How we are going to specifically target? I'm sorry, I'm not a
No, actually,
cancer
the thing
biologist.
goes like that,
Yeah.
that our ultimate goal in this case, in this particular case,
Correct.
is FDG, means a glucose which is radioactive.
Yeah.
But in glucose, this only fluorine 18 can be attached. But how will you get this fluorine? Fluorine can be attached using some chemical reactions,
Yeah, yeah.
some ionization technique.
Yes.
This fluorine 18 cannot be produced using normal oxygen that we are having, means oxygen 16. So for that, very special water is used, where this concentration of oxygen 18 is higher.
Oh, I see.
So using that water, we produce this F18.
Okay.
So the requirement comes from the ultimate use, what exactly you need. So then ultimately we comes to oxygen 18. How to convert it? There this accelerator
Got it.
helps.
Got it. Thank you very much. Thank you so much.
Sure. Please.
It's a very interesting topic, and we are getting illuminated by the things what BCC is doing. But one applications you are showing that it is applicable, that the radioisotopes for fertilizer and some nutrient management, like that the agricultural applications. Can you please highlight few points? How can we measure?
Actually,
that
this particular topic is also new to me. I just heard from somewhere that it can be used. Or it will be used. So I do not know. Truly, I do not know
but
the
what,
details
what,
in that.
what we can think of that, because the Indian community is struggling for the development of our indigenous sensor. So basically, whenever we are going to sense anything, so we have to depend on the imported item. So if we think that this isotope if it can be used for the fertilizer or NPK detection, and likewise the different aspects of the agricultural applications that we can think of, that whether we can use these isotopes or not.
I would say these isotopes will not be directly used in that sense.
But
yes,
indirectly.
indirectly, you can have some tests, you can have some quality assurance, you can have some genetical change. Just to give you an example, we are using radiation. Generally, radiation is treated as quite hazardous things, but the same radiation we are using through the byproduct of our reactors, cobalt-60 and all, for genetic mutation of different seeds. It looks quite horrible, no? जिस चीज़ से कैंसर हो सकता है वही चीज़ आप हमारे सीड्स में डाल रहे हैं. But no, lots of farmers in Maharashtra, they have used those seeds and they are having tremendous crop. So some or other way we can use all this technology, radiation technology, this isotope technology. The particular field that you have mentioned, I am also new to that, but somehow, direct or indirect, it can be used. Few more?
Yeah, sure.
Thank you very much, Dr. Chadha. You have taken me back to 1972 when I used to visit that area. Although I started in Simplex in 1961, but I was very young. How much? I was 29 or 30 at that time. And you have rightly said, full of snakes, jackals, foxes, and so many things. Even in some area there were crocodiles.
Yes.
But we had to work in that, and it was very fascinating. And this stage is very fortunate to have, and we have met Dr. Bose, Satyen Bose was here. Dr. Nak Chaudhary was here. And I was fortunate to meet Dr. Raja Ramanna.
At that time, I think.
No, much after that. And I met Dr. Kalam. And very interesting thing about these scientists is, I went to Dr. Raja Ramanna to give me an article. We were preparing a collection of articles on Indian culture when we went to scientific topic. He said, no, I will not write on atomic energy or anything like that. If you agree, I will write on Rag and Raganis of India. So this is another very fascinating aspect of these scientists. So it was all very nice of you. You may have a lot of questions. I also have a lot of questions. If you can forward it to us, we will redirect it to Dr. Chadha, or you can directly correspond with him or write to him. And you see, only 2 days before, I was at Tata Medical Center, and we were discussing about particularly the oncology department and what is required, all these further research which they are doing. So one day it will be very interesting if Dr. Chadha and others from his department and oncologists and doctors in Calcutta, they can sit together and find out the solution of their problems. And this is what the whole idea is of coming together and meeting here. Like that, I also have certain queries. I will put up to Dr. Chadha, I will write to him. Thank you very much, Dr. Duwari and Dr. Chadha. And thank you, Dr. Maiti, and all the guests who have come here. Please do take dinner with us, and we can interact there.
I think the formal vote of thanks, we will have it from Raj Gopal Sureka ji. So I request him to give us formal vote of thanks to everybody and to the speaker.
मैं आप सभी सज्जनों का जो आज हमारे संसद में पधारे हैं, सबको मैं प्रणाम करता हूँ. आप लोगों के आने से ही हम इस गतिविधि को आगे बढ़ा सकते हैं. और ये आज के लिए, आज की परिस्थिति को देखते हुए लोगों का संपर्क, खासकर वैज्ञानिक जो गतिविधियां हो रही हैं, जितनी खोज हो रही हैं, हमें पता ही नहीं है कि क्या है। आज आए तो डॉक्टर चड्ढा साहब से सुना, इसके पहले भी जितने अपने ये इस तरह के जितने फंक्शन हुए थे, उसमें हमने कुछ ना कुछ नई जानकारी तो सुनने को मिली ही है। आज इस चीज़ की बहुत ज़रूरत है। साधारण आदमी अब धीरे धीरे जानकारी इकट्ठा नहीं करता है, क्योंकि उसको यूट्यूब में मिलती है, और यूट्यूब में मेरे को जो लगता है कि यूट्यूब में अधिक से अधिक जानकारियाँ कन्फ्यूज़न ज़्यादा करती हैं। अगर डॉक्टर चड्ढा की तरह और भी हमारे विद्वान आएँ और उसके साथ आप अगर आएँ तो उसकी प्रतिष्ठा और बढ़ जाती है। मैं चाहता हूँ कि इस तरह के प्रोग्राम होते रहें, आप आएँ, मैं आप सबको प्रणाम करता हूँ, धन्यवाद देता हूँ। धन्यवाद।
I think the accelerators are waiting for the society at VECC, but just around 10 feet from here, the Hibadas and other things are waiting for all of us.